Hi, this is Paul from Foresight Tech. In this video, we are going to deal with the representations of functions as a power series by manipulating geometric series and using term-by-term differentiation and integration. Let's see the outline. First, I will introduce geometric series representation, and we will practice two questions together about how to manipulate the geometric series. Then I will introduce term-by-term differentiation and the integration theorem, and we will practice another two questions together about how to use the theorem. Let's see the material. Here is a geometric series representation, and can we see, and this type of reciprocal function 1 over 1 minus x can be represented or expressed by a geometric series, right? This is an important power series representation, and 1 over 1 minus x is a special type, one of the most important. And how about the other functions? Okay, definitely we have other power series representation, and I will introduce other important power series representation for other functions and later in other videos, especially in Taylor series. Okay. And first, let me show here now y, and we have this function to be represented as the power series. Okay, if we look backwards, okay, from the right side to the left, see this is what is geometric series, and we learned that before we can find the sum, right? If we find the sum, this function is just the sum y. Okay, of course. This geometric series, what do we have? We have a equals 1, right? R, the common ratio, equals x. Therefore, follow the formula as the sum is a over 1 minus r, right? Therefore, equals 1 over 1 minus x. Can you see that's the function? Of course, we have a domain. We learned that before. And is the absolute value of r less than 1, which is a absolute value of x less than 1, right? And when, and usually we call it what? We call it if and only if. Okay, there's a if and only if. You know, other than this case, other cases diverge. So there's if and only if. We can say r equals 1, the radius of convergence, right? And we can say the interval of convergence is -1 to 1. Okay, that's the only convergence interval. Now, I will give you one remark. And this geometric series representation only represents 1 over 1 minus x. How about the other function? Yes, we do. If other functions are linked to this type of function, okay, so we can try to manipulate the geometric series. Therefore, we can find other representations for other functions. Let me highlight this. So manipulate the geometric series. Okay, so now let's go on to practice questions. How to manipulate? Here is the first question. We need to find a power series representation for this function and find the interval of convergence. And how about this function? And this is not 1 over 1 minus x. However, is linked to that function, right? So let me draw here. Is definitely linked to this function. However, this function, let me see. This function, we can have a geometric series representation. If I wrote it is n star from 0 to infinity, x raised to the nth power. Okay, the domain is absolute value less than 1. Now the question is how to link. Okay, I will see the difference here to here. So we need to manipulate it. Okay, just all we need to do is manipulate. Okay, it's not difficult to manipulate. Let me show you. Okay, in this 1 plus x squared, that's the beginning. We can do this 1 over 1 minus negative x squared. That is the same? Yes, of course. And then we see this is x, or we say this is u. See, if I put a u is a negative x squared, see, what do we have? We will definitely have a 1 over 1 minus u, right? Therefore, is the form of geometric series representation. Okay, of course, we do not need to exactly put the u. I will directly see negative x squared as u, or as a term. Therefore, we can get the representation in this way. So n start from 0 to infinity. Now, no longer x, but a negative x squared, right? Does this make sense? Okay, because what? Negative x squared is u, or you just see this as a group. Okay, now I just simplify a little. Okay, we have a negative 1 raised to the nth power times x squared raised to the nth power, which is 2n. This is n start from 0 to infinity. Is this a power series? Yes. Now we have a power series. If I'm going to open this, see, we will have this. The first term is 1. The second term is negative x squared, and then x4, and then negative x6, and then x 8th power, okay, and then goes on. Okay, this is a interesting series, right? What we left now is the interval of convergence. Let me show you how to get the domain, or the interval of convergence. And all we need is use the results. Okay, we see this series converges. Okay, so when this condition satisfied, negative x squared, you know this is u. And then see, if we use these results, this means what? The domain is absolute value of u less than 1, right? Therefore, is this less than 1. Okay, so we need to solve this inequality. Easy to solve. Okay, if we solve this, what do we get? We get absolute value of x less than 1. And this is the domain. This is the interval of convergence. So let me write down. Therefore, we find that the interval of convergence, okay, of the series we got is this, is a negative 1 to 1, is open interval, right? So here is the first question. Let's practice one more question. Here is the second question. And this time we have this function. See, a little bit of difference. Okay, we see the top, we have a function x, but don't worry. Okay, so this x does not matter. We don't need to change anything to this part, because this x is already a power, right? Okay, so our function is still linked to geometric series representation. Okay, so let me highlight this, which means this is still linked to 1 over 1 minus x. And you know this is x raised to the nth power. Okay, and the domain is still x less than 1. Okay, I will show you how to manipulate. Of course, all we need to do is change it to this, to negative x, right? See, very similar as the first question. Okay, so let me show you. Here is x over 2x squared plus 1. We need to change a little. Okay, so first, this x does not matter. We'll take it down. So x times 1 over, now I switched the order of this addition. So that's 1 plus 2x squared, right? And I change it to 1 minus negative 2x squared. You notice the same. Then now, see, if I highlight this, set up this is u, therefore directly go to 1 over 1 minus u, right? You know, is just do this substitution. U is negative 2x squared. Okay, so this time definitely we can expand. into power series. Okay, this should be negative 2x square parenthesis nth power, right? If you want to rotate the index n start from 0 into infinity, almost, right? And then we change a little to get a form. Okay, so sigma is negative 2, right? Coefficient raised to the nth power, and then times x. X raised to the 2th power raised to another power is a power, so we have 2m. So how about the dx? Okay, and the dx we can times another x, put all the x together. See, we have to add 1. That doesn't make sense because we have 1's power outside. Okay, so if we use the distributive, so the new power goes to here. We just merge all the x together. Can you see what do we get now? We get this power series. Okay, so this is the way. Okay, so how we get the power series? Now the same, we're going to look at the domain. We know this series converges. Okay, so dr do this. U, absolute value of u less than 1, right? U is negative 2x squared. Okay, so this inequality we need to resolve is from here. Okay, and then we solve this, see what do we get. Easy. Divided by 2 both sides, and then take a root, square root. Therefore we get an absolute value of x less than square root of 2 over 2. Okay, that's the domain or the interval of convergence. Therefore we wrote it down. So the interval of convergence now is this. Our convergence is negative square root of 2 over 2 to positive square root over 2 over 2 is the open interval, right? Okay, that's almost the same with the first questions. No big difference. Now we have these questions. If we have other type of functions not linked to 1 over 1 minus x in this way, how do you find the power series? We do have other tools. Let me introduce one. We call the term by term differentiation or integration. Here is the term by term differentiation and the integration theorem. And what does it mean? Let me highlight and these keywords, term by term, which means we can do term by term differentiation and term by term integration, right? Okay, and let's look at it. The first, if we have a power series, we call it the original power series. How to take a derivative? Okay, and the derivative is just a word, term by term. Can you see the derivative goes inside? Therefore, let me highlight. So this is the major one, that the meaning. And each term is a power series as a power function, and the take derivative is the power function. Therefore, easy to find, right? Okay, so that's the meaning of the term by term differentiation. The same for term by term integration. Can you see? If we're going to integrate the original power series, and we can integrate each term first, and then take the summation, right? And each term is a power series, integral and that derivative is the power series. So we can get the answer. The plus c, you know, this is all the constant numbers, right? Let me highlight the second part, which means we can do term by term integration. Okay, and another remark, can you see the radius of convergence remain the same? Because so these two formula, we have two power series, the original power series and the new power series, and this theorem gives us both power series has the same radius of convergence. Okay, so this is important. Okay, later we're going to use this. And the second, the new power series, okay, represents the derivative or the antiderivative of the original function. What does this mean? Derivative or antiderivative of the original function. Let me set up, okay. If this is the original, okay, we say fx, okay. See, and the first formula give us, if we need to find the derivative of the original, can you see? And the final one is equal to here. And the derivative of fx is where? Is the new power series, right? Therefore, the new power series represented the derivative of the original power series or the original function. The same and the integration. Can you see? If we need to integrate the final is what? Okay, here is just the antiderivative of fx. Is this true? Yes, because the original is the integral of fx, right? And the final new power series is just represent the antiderivative of the original function. What does this really mean? Really means this kind of okay tool. See, if we need to find a power series for a derivative, what do we need to do? We only find the representative for the original function and then take a derivative term by term. Okay, so this is a tool. The same, if we need to find a power series representation for the antiderivative, what do we need to do? We need to find the power series representation for the older, for the original, and then integrate term by term. Okay, so this is a kind of tool. I cannot give you a proof here because we need other new knowledge. Okay, so for the series of functions, which is not covered in our textbook. However, I will give you a kind of meaning. Can you see? If I change this summation to finite term, that's true, right? We learned that we call the linear property for differentiation, linear property for integration. Okay, and all these formula give us is just the finite term can change or extend to infinite term, and these linear properties they are kept. Now let's go on to practice. Here is the question. We have this type of function. Okay, so this is not a reciprocal function, right? Therefore, we cannot use the geometric series representation directly. However, we can see, okay, so our function is linked to this function. Okay, 1 over 1 minus x parentheses square, right? Okay, that's easy because this 4x just change to negative x. And for this function, we have another link, okay, which is the derivative of reciprocal. Therefore, now that's all we need. See, we have a power series for the reciprocal, right? Geometric series representation. And we use a term by term differentiation. We can find the representation for this function. And we use the link, we can finally find the representation for our function. That does make sense? Okay, that's the idea. Therefore, we need 2 steps. The first step, find the representation for this function. The second step, find the representation for our function. Okay, so let me go to the first step. So we need to find the representation or power series representation for this function. Okay, for 1 over 1 minus x squared. How? And all we need is what? Is a term by term differentiation, right? This term. What do we need? 1 over 1 minus x squared equals the derivative of 1 minus x. Take a derivative. And if we wrote into power series, which is x raised to the nth power, take a derivative, right? Let me write the index, which is from 0 to infinity. And then now, this step, we can go term by term differentiation. Each term is a power. See, this take a derivative. The index is from 0 to infinity, we know. And this step is what is term by term, right? Differentiation. Okay. And now we can find the results. So this take a derivative goes to n, and the power goes down n. That's normal. However, a little bit of difference here. Okay, so n is started from 1 to infinity. You will say why this is started from 1? Because the first term is 1. Take a derivative goes to what? Goes to 0. Disappear. Okay, so that this makes sense. Therefore, what do we get? We get a power series. Good. Let me call this is the power series 1. And then now what we left is the domain, right? We need to look at the domain. The term by term differentiation theorem give us, and this is the old series, and our power series 1 is the new series. Both theories has the same R, right? The same radius of convergence. So let me write down that first. So R equals 1. How about the endpoint? Okay, the theorem did not say, so we have to test separately. Okay, let's look at the endpoint, which means when x equals positive 1 or negative 1. See, we have this time the general term. Okay, so easy to see this does not approach 0. Why? If x equals 1, this diverges to infinity. If x equals negative 1, this is oscillation, right? Okay, so the limit does not exist, therefore not approach 0. And so we know the first series diverges. So remember, how did we get diverge? Because we have this theorem, right? Test for divergence. Do you remember this? Okay. Therefore, what do we have now? So we have the domain. So the interval of convergence. The interval of convergence this time is what? Is a negative 1 to 1 open interval. Of course, let me mention this is for the first power series. Now we can go to the second step. The second step, we need to find the power series representation for our function. Okay, let me write. We need to find the power series representation for our function. So our function, okay, is this x over 1 plus 4x squared. Okay, and then let me copy what we discussed before. So our function is 1 plus 4x parenthesis square, and this can link to this function, right? 1 over 1 minus x squared. And this function, in the first step, we already got the representation, which is n times x raised to the minus 1's power. Okay, n start from 1 to infinity, right? And the domain as x belongs to negative 1 to 1. And we call it this is a series 1, right? Okay, so now the second step we need to do is just do substitution. Okay, so this is all the stuff. Let me show you. What we need to do is do this x over 1 plus 4x squared. This is our. Okay, let me change it a little. 1 over parenthesis 1 minus negative 4x parenthesis square. Can you see? Okay, so they are the same, right? Now we can do this. We see this negative 4x as a group. Therefore, we can use the results from the power series 1, right? Okay, directly let me write what's the one we need, which is x dx times summation. Okay, n times x is no longer x, but negative 4x raised to the n minus 1's power, right? And the index n from 1 to infinity. Okay, so you know this is just use the results of 1. Now what do we do? Okay, so we just simplify. Okay. And we also merge x together. See, what do we have? This is not difficult to get. And then now we finally have this summation. N start from 1 to infinity. And the constant number negative 4 raised to the power of n minus 1, right? We have a coefficient n, so times m. And how about the power? X raised to the power now is what? Is a power of n. Why? Because see, x raised to the power n minus 1, but the outside we have another power. Okay, so 1 plus n minus 1 is m. Okay, so let me hide. Be careful about this. Okay, therefore, see, and this is power series, right? And this is already a power series, and that's the power series we need. Let me call power series 2. Okay, now what we left is talking about the domain. Okay, so how? Remember, so now the domain, okay, so for our power series, it comes from the power series 1, right? So we have to use the domain from the power series 1. Okay, therefore, if I wrote is this. So our power series 2 converges. Okay, when negative 4x, right? If you see, because this is the substitution. Okay, if I wrote this is the substitution, which is we need to follow this domain, right? So negative 4x should be belongs to negative 1 to 1. Does this make sense? Okay, and this we can solve, right? So we can get the detail for x. This means x belongs to negative 1/4 to 1/4. See, that's the domain or the interval of convergence. Okay, therefore we find, so the interval of convergence for our series, okay, is negative 1/4 to 1/4. Okay, so keep in mind that this is the final. Okay, so the domain for 2. That's the answer for this question. Let's practice one more question. Here is the last question, and then we see our function. Okay, so x squared does not matter, is already a power, right? So we need to do what? We need to link arctangent, finally go to what? Go to geometric series representation. So how to do? It's very similar as the previous question. So let me show you the link first. And this function is linked to arctangent x, y, right? If we see x squared, okay, is u, so then we link them together. How about the arctangent? Arctangent is what? Is very special, okay? And if you remember, arctangent is what? Is an antiderivative of 1 over 1 plus x squared. See? Okay, and then this integrand, okay, we can link it to what? Reciprocal functions, which is a geometric series representation. And then now we can see, because we have a representation for this, therefore we have a representation for the integrand. And then we use a term by term integration, therefore we have power series representation for arctangent, and finally we have the representation for our function, right? This is the idea. So we go 2 steps. The first, so we find the representation for arctangent, and then the second step we find the representation for our function. Okay, so let me do this. So the first, we find the power series representation, okay, for arc, right, which is a inverse tangent. Okay, how to do? So we already showed. So all we need is directly. Let me go. Arctangent x is the antiderivative of 1 over 1 plus x squared, right? And change a little bit. 1 minus negative x squared. And you can see now if I highlight this one to substitution, and that's directly linked to the geometric series, right? So I will use the geometric series representation. Can you see? And we can find. So this type of, so the summation, right? Negative x squared raised to the nth power. Okay, the term is from 0 to infinity. Okay, and here is the original x, right? Okay, so now what do we do? I will do one more step. I will take a -1. Okay, is the constant number wrote into this way. So I will write, which is a summation -1 raised to the nth power. Okay, x raised to now is 2 nth power, right? Okay, n is from 0 to infinity. And what do we do now? Okay, definitely. Now is what? This is the integral of power series, right? So we can do integration term by term. So let me put here. Now let's do term by term integration. Okay. See, now what do we have? We have this. The integral -1 raised to the nth power x 2n dx. Okay, n from 0 to infinity. Now easy, right? So each term, this integral is a power. Okay, so the antiderivative is still power, right? So let me write down. If we do calculation, now we get a -1 raised to the nth power. Okay, times and the power plus 1, right? Increase 1, and over 2m plus 1. And the term is start from 0 to infinity. Of course, don't miss plus c at the end. Okay, so now what do we get? This is a power series. Good. That's the power series what we need for arctangent. So this is not for our final. So let's put 1. We need to talking about the what domain, right? Okay, so this time. Before we talking about the domain, let's talking about this c. We do not like a constant number, and we should find out what is the constant number. Okay, so this is easy to find. What do we need to do? We just put a special value. Okay, like I put the x equals 0. Okay, into this equation, both sides, and then we can find out what is c. Let me put this special. Put x equals 0 is okay, right? Into the first series, power series, and then we will find the c equals. Can we see arctangent that the 0 is 0? Okay, put the 0 here, all the term is 0, right? Therefore, c is what? Of course, 0. Good. So this is easy. So we find the c equals 0. And which means what? Our power series, we don't have the constant term. So now we're talking about the domain. So first, we know 2 series keep the same r, right? So r still equals 1. And how about the endpoints? -1 and 1. So we look at x equals +1 or -1. And we see both case. And the first series converges y. Okay. And let's look at it. If x equals 1, okay, this is 1. And this is what? This is an alternating series. And the absolute value is 1 over 2m plus 1, decreased to 0, right? So by alternating series, this is converge. The same if x is -1, so this is -1. Okay, -1 take out, so is what? It's a Dia alternating series. We use this. So let me see. What do we get? This is by alternating, right? Alternating series test. Therefore, what do we get? Now we get the domain or the interval of convergence. Now is the interval of convergence. Okay, is what? Is -1 to 1 include both endpoint. Okay, and let's mention this is for what? For the first power series. Now let's move to the second step. The second step is to find the power series representation for our function, right? So let me write here. Now we can find the power series representation for our function, which is x squared times arctangent at x raised to the third power. Okay, let me copy what we discussed before. Our function x squared. So let me put it here. Our functions x squared times arctangent at x raised to the third power. Okay, so can link it to arctangent x, right? Because if we do substitution at that, so we can link them together. And we already got the representation for arctangent from the first step, which is this. -1 raised to the nth power times x raised to 2m plus 1's power over 2m plus 1. And n start from 0 to infinity. And we are the domain, so we just get x is belongs to -1 to 1, close the interval. Okay, so this is the power series 1. Now, let me go into do manipulation. So for our series, which is x squared times, this is our function, right? Okay, and if we do what? We say do substitution. Let me still put here, so u equals x the third power. Therefore, we have arctangent u, right? So we can use the results. So this one should be equals. Okay, so I miss x squared. Let me put x squared is outside, does not matter. Okay, so now is a summation. So -1, we use the results from 1 raised to the nth power. Okay, so I times x the third power raised to 2m plus 1's power, right? Over 2m plus 1. You know this is true because this is u, right? Let me put the index n start from 0 to infinity. But now what do? We can simplify a little. Okay, so we put all the x together. Imagine how many x do we have? Okay, so the constant -1 raised to the nth power still here is times the denominator is still 2m plus 1. Okay, numerator is x. Imagine what is the new power. We have a 6n plus 3 but don't miss these 2, right, outside. So 6n plus 5, finally we have this. Let me put it is 6n plus 5. Okay, let me highlight it, this one. Therefore, what do we get? This is the power series, right? This is the power series, exactly what we need. Let me call this is 2. That's the one we need, right? Okay, so what we need to do left is talking about the convergence, which is the domain. We know. Now this power series converges. What? Okay, so when x the third power belongs to -1 to 1. Okay, let me highlight y. Because x with the third power is just the u, right? See, the original u is here, the domain belongs to -1 to 1. So therefore, this is true. And we solve. See, we definitely find out what is x. X still belongs to -1 to 1, include -1 and 1, right? This is the domain. So we conclude finally the interval of convergence now, okay, is what? Is this -1 to 1. -1 to 1. Of course, so we mentioned this is for our final, which one is 2. And that's the results for this question. That's all. Thank you. I hope you enjoy learning on this topic. If you have any question, please leave your comment. If you like this video, please give me a thumbs up. Thank you for your support. Please don't forget, you are very welcome to subscribe to my channel for more videos. In the next video, let's see, we will move to Taylor and the Maclaurin series, which is the last section in this course. Hope to see you there. Thank you. Have a nice day. Bye.